Hey everyone, I'm Miss Hu, your physics teacher. In this video, we're going to go through the concept of the detection of radioactivity. This is a topic in both the SPM and IGCSE physics syllabus. There's of course a lot more to know about this topic, so if you'd like to find out more, please feel free to do your own research or watch my other educational videos. What we'll be covering in this video are the information that you would need in order to be able to answer the questions in your examinations. So what we'll be going through are the background radiation, detection with a detector and counter, as well as a concept of the corrected count rate. So first things first, what is background radiation? Now we have to know, first of all, what is ionizing radiation? Ionizing radiation is radiation with high energies that can knock off electrons from atoms to form ions. So the concept of ionizing means to be able to form ions, not the radiation itself becoming an ion, but the radiation forming ions from other particles, which means that when the radiation is released, for example, into air, this radiation is able to make those air particles become ions. So that's why it's ionizing. So the radiation is ionizing the air particles, hence known as ionizing radiation. So what you should know in your syllabus is that ionizing radiation is synonymous with radioactive radiation, which means that whenever we use the term ionizing radiation, we are in fact referring to radioactive radiation. What has this got to do with background radiation? So background radiation is ionizing nuclear radiation in the environment when no radioactive source is deliberately introduced. What that means is if you are in an environment where we know, okay, there's no highly radioactive material. So for example, it could be a normal situation like you're at home, you're in school, in the office, in a shopping mall. But if you were to use a detector to try to detect this ionizing radiation or radioactive radiation, you'll find that, oh, there's a value there. And that's because there is a lot of naturally occurring ionizing radiation. There's a lot of naturally occurring radioactive radiation. So because this radiation is already in the environment, it's in the background. That's why it's known as background radiation. It's already existing in the environment, even though there's no radioactive source that we put in there and we're like, okay, now let's make this place radioactive. You don't even have that, but that location is already in itself radioactive. So yes, that means you are actually living in, working in, studying in, breathing in a place that is radioactive. But don't worry, the radiation that exists is a very low level, which we are already used to and have adjusted to. So don't have to worry, you're not going to be, oh my God, exposed, overexposed to a lot of radioactivity. No, this background radiation is a low level that we are already used to. Where on Earth does this background radiation come from? So like I mentioned just now, it comes from everywhere around us. So it could come from the gas in the air, for example, radon gas. It could come from the food and drink that we eat and drink. It could come from the rocks and building materials. It could come even from the furniture that we are working on and we're sitting at. It also comes from the cosmic rays from outer space, from the sun and from all the natural satellites that are orbiting the Earth or somewhere floating and moving around in space. Yeah, it also could come from that. So background radiation could come from any of these sources. So how do we detect radioactive radiation? There are actually a few devices which can detect radioactivity, but we will only discuss one in this video. And this is the only one that you really need to know for your examinations. This is the most commonly used radioactive radiation detector. And the reason why this is the most commonly used is because it is one of the best. It is quite accurate and it's also able to give an immediate notification about the detection of any radioactivity present. This is the Geiger-Muller tube, also known as the Geiger counter. Now the Geiger-Muller tube, short form, you can say GM tube, is actually this part of the machine, and this GM tube is connected to a counter. How it works is we point this end of the GM tube to the location or the material or the area where we want to detect radioactivity. So what happens is the radiation would enter the tube. There is some reactions or rather interactions that happen here that causes the detection to occur, and then this information is portrayed on the counter here. So you can see on the machine, there is a scale which shows us a bunch of numbers, and this is how we're able to detect radioactivity. So of course, to find out more about the Geiger-Muller tube and how it works, I'm not going to discuss it right here in this video, but please watch my other videos where I do discuss how the Geiger-Muller tube works, as well as other devices that can detect radioactive radiation. For now, let's just focus on this machine. So what we have on screen here, you can see there's a scale, and this is why the Geiger-Muller tube is used so heavily. It's so useful because, for one, it's able to show us numbers. It's able to show us how radioactive that particular thing or object that we are detecting is. You can actually record numbers from here. And this machine is normally set up with a sound as well, like a buzzer. And this buzzer will make a sound when it detects the numbers. So that means the higher the number, the greater the sound. So that's why when you watch movies or shows where they're trying to detect radioactivity, you find them holding the thing and it's like, and then it starts to get a higher pitch when it detects an area where it's highly radioactive. Yes, that's a Geiger-Muller tube. So when it makes a high pitch sound, that means that the radioactivity level is very high. So the greater the radioactivity, the higher the pitch of the sound. So that's why the Geiger-Muller tube is very useful. It's able to give us an immediate notification in terms of numbers as well as sound. How these values are portrayed, they're usually measured in counts per second or counts per minute. So what we mean by counts over here is it's not very straightforward. It's not that, oh, it detects one piece of radiation, that's one count. It's actually more complicated than that. But generally, how it works is with the ionizing that happens inside the GM tube. So the more ionizations that occur, typically the higher the value that you would see over here. So we display the numbers as counts per second because we don't need to know, oh, what's the total number? Because if you have a total number, then it's very misleading because it's just accumulating in terms of the numbers, like, oh, it detects 1, then 2, then 3, then 4. But you need to know how much time it took to detect those numbers, right? So that's why we count the average per time. So how many counts are there per second? How many counts are there per minute? So we have these two options because if it's extremely radioactive, it can give quite a high number every second. But if it's not that radioactive, that means there's less counts per second. So we count it per minute over a span of 60 seconds instead. So either one works, depending, of course, on the level of radioactivity that we are detecting. So this is typically what the Geiger-Muller tube with a counter look like. There are also different variations of the machine, but they essentially work the same way. So for example, we can attach the tube over here. So when you hold it, you're holding the counter together with the tube and you just point the tube towards the area which we want to detect. There's also a handheld Geiger counter, as you can see over here. This is a much smaller, more portable machine which is easier to hold and detect. Now, when detecting radioactivity, we have to keep in mind that background radiation will always be there. So let's say we want to detect the value of radioactivity of the radioactive material, meaning we want to see how radioactive that material is in terms of the counts per second or counts per minute. So when we point the Geiger-Muller tube with the counter towards the radioactive material, we must remember the number that we see here is not only from the radioactive material. Background radiation is always present wherever we are, right? Remember, the background radiation can come from anywhere around us, from the air we breathe, the food and drink, the building materials, cosmic rays. It's always there in the environment. And you can't, like, hey, let's exclude this number. You can't. It's always there. So when we use the counter and the GM tube to detect radiation, the readings that we get comes from two sources, the background radiation as well as from the radioactive material. So if we want to obtain the radioactivity of the radioactive material only, we need to correct the count rate. What do we mean by correcting the count rate? We need to minus the background radiation. So in order to do that, first of all, we need to obtain the value of the background radiation. So first of all, switch on the Geiger counter without the presence of the radioactive material. When we do this, we have to take the value of the background radiation off that position where we are at. So let's say, for example, we're out in the field and we found a piece of radioactive material and we want to determine, okay, what's the level of radioactivity of that material? But before we even do that, we need to know what the background radiation is. That means without that radioactive material near the machine, switch on the Geiger counter and take the reading. Okay, what is the reading of this area's background radiation? We need to do that because every location has a different value of background radiation. So you can't like, okay, let's switch this on in the lab. Oh, okay, that's the value. Then when you go out to field, you take that number and minus the background radiation of the lab. You can't do that because different areas have different background radiation. And that's because different areas have different things present, right? Because in the lab, you have the values from the building materials, the furniture, even food and drink. You're not supposed to have food and drink in the lab, but maybe somewhere beyond the screen, somehow it's able to pick up the value somehow. You never know, right? Even the people who are there, the air we breathe, right? All of these are contributing to the background radiation in the lab. But when you go out to the field, there's different things there. You have different rocks, you don't have the same buildings, you don't have that furniture there, you don't have the food and drink there, you have different people, different air. So different places have different background radiation. So we need to take the value of the background radiation of that location first, then take the reading of that radioactive material, and then that reading needs to minus the background radiation. So when you minus the background radiation, that will be the actual value of radioactivity of that radioactive material only. And that's the corrected count rate. And that's the end of this video lesson. If you found this video educational and helpful, please click like and subscribe for more video lessons from your physics teacher, Miss Ho. Happy studying!